Okay, so I'd like to start off by giving you a little bit of insight into why the time-ordered product is the nice physical one to consider. So we've always been drawing our space-time diagrams with t increasing up the page and x increasing across the page. So let's now imagine a situation where we're going to have some particle scattering. And the first particle, perhaps, was created at space-time event x1 mu. So that was the earliest time. Then we had another particle created at x2 mu. They got close to each other. They interacted in some way, and they produced another two particles. One was detected at x3 mu, and another was detected at x4 mu. We start from the vacuum state. In the very far past and in the very far future, we return to the vacuum state after we've detected our two particles. Good. Okay. So now, how should we describe this experiment? Well, we start with the state, the vacuum state, kept vacuum. Then the first thing that we do is we create a particle. So we do that by acting with phi of x1. Then we create a second particle, which we would do by acting with phi of x2. Then we detect a particle at space-time event x3. To detect a particle, to destroy a particle, we act with phi of x3. And finally, we detect our final particle at space-time event x4, and we compute the overlap with bra vacuum. So this is the Lorentz invariant amplitude that would correspond to this picture up above. Now notice something. T4 is the greatest time. It's greater than T3. T3 is greater than T2, and T2 is greater than T1. So the amplitude that we have just written down is time ordered. And what's going on? Well, we like to do the earliest stuff first. So the earliest operators act on the vacuum, and the operators that come last, the latest operators, they act on the state that's already been produced. And that's why we put latest leftist. Okay, so this is really the explanation of why the time-ordered notation is the physical one. So we're almost done. Just one more thing I want to ask about time ordering. And what I want to ask is time ordering well defined? And here, specifically, I'm worried about Lorentz invariance. So we want to build a theory that is Lorentz invariant. So, we can time order things in one frame. Will we get the same answer in some other Lorentz frame? So when I'm asking, is time ordering well defined, I'm really asking if it is Lorentz frame independent. So do we get the same answer in any Lorentz frame? Okay, that's what we want to ask. Okay, so now why is this an issue? Well, let's imagine that we're in some frame with this t, and here is x. We have one event, which is over here at 1. Here is the light cone. There we are. There's the one leg of the light cone. Here is the other leg of the light cone. And we're going to put the second event over here, too. So in this frame, if you say to me, what is the time order of the product? 5x1, 5x2. Well, who's latest? That's T2. So this would be phi of x2, phi of x1. But now I'm going to imagine doing a Lorentz boost to a second prime frame. In the prime frame, this is t prime, and this is x prime. And if we now take a look, maybe let me redraw that axis. I don't know. Okay. Maybe that's a bit better. This is x prime. Now just take a look. If these lines, if I draw any lines which are parallel to x prime, these are all lines of constant t prime. So in the primed frame, you see, event 2 is earlier than event 1. So this is in the frame, Tx, but this is in the prime frame. In the prime frame, 2 comes before 1. So in this situation, somebody sitting in the prime frame would not agree on how the operators are time ordered as compared to somebody in the original frame. Now, the point here is x1 and x2 are space-like separated. And because of that, phi of x1 and phi of x2 commute. So in actual fact, no problem. We've written down the same product in the frame and the prime frame because these two operators commute. But we were saved by the fact that these operators were space-like separated. If we consider a case where they are time-like separated, they don't commute. So here is t, there is x. To get two operators that are time-like separated, so there's operator 1, here's the light cone, and to get something that's time-like separated, I should put operator 2 inside the light cone. If I now move to the prime frame, well, there is t primed, there is x primed, and the light cone inside the primed frame is exactly the same as the light cone in the unprimed frame. You know, the light cone is the one thing that all inertial observers agree on because the speed of light is a constant in all frames. And because of that, if we now take a look at the slices of equal times in the primed frame and the original frame, they both agree. So in both frames, that's in both frames, T2 is greater than T1. So, and this is in the case where your 2 points are time-like separated. So when the two events are time-like separated, everybody agrees on how they are ordered, and that's good because these operators don't commute. So in both frames, if you are writing down the time-ordered product, in fact, you would write down phi of x2, that's the latest time, and then phi of x1. In contrast to that, if your two operators are space-like separated, not all observers will agree on how the times are ordered, but that doesn't matter because the fields commute. So if the fields are space-like separated, the time order is not well defined, but no problem because the fields commute. So that's not an issue at all if the two fields are time-like separated, then the time order is well defined, and you get the same time order in the original and the primed frames. And that completes our discussion of time ordering. All we have left for this chapter is to discuss the exercises.